we can write a general rate equation, which, for example, if we have a reaction that goes from A, where A is the reactant, A is consumed in this reaction, we can usually write this rate equation as dA over dt. That means a very small change in the concentration of A in a very small time unit. And for those of you who have done maths A-levels, you will see that this is already the start of a differential equation. But let's not worry too much about that. And we can describe that by an equation and where we have a rate constant, K. And when we are talking about the consumption of something, the whole thing gets a negative sign, so minus. So every time something is consumed, it gets less and therefore gets a minus. Times concentration of A to the power of, let's call that M. So this guy here is a constant. And this guy here is what is called the rate order. And I think in one of the videos last week, I pointed out that the rate order is nothing but a mathematical concept. It has nothing to do with how many reactants actually bump into each other or react with each other. What is this called? Loud? That's the molecularity. And I told you in the video that molecularity is either 1 or 2. And in very extremely rare circumstances, it can be probably 3. A molecularity of 0, for example, doesn't exist because you can't have 0 reactants bumping into each other. Nothing would happen. Or a molecularity of, say, 1/2 or something like that doesn't exist. Whereas a rate order can be any number that you can think of. Negative, positive, can be 0, can be God knows whatever you want. So I think I want you to be aware of that. In another video, I explained to you how we can look at, how we can find out the order of a reaction. And I told you that basically we can write it as also, well, technically it's a little bit dodgy, but there is a reason why I do that. We can write this as speed of the reaction. And I want you to be aware what the difference is between speed and the rate. What's the difference? The direction, exactly. Speed basically has no direction, whereas the rate, in this particular context, has a direction, where we have this plus and minus. Speed doesn't have that. And so if we write speed of a reaction equals K times A to the power of M, we can convert this. We can take both sides log. So we would get log speed equals log K plus M times log A. Yeah? And this is the equation for a straight line. So this is y equals c plus mx. And all I need to do in order to find the order of a reaction would be I need to plot my log speed versus log A. and, bless you, and I would get a straight line, hopefully, like that. This line can be in the negative range. It's not a big problem if it is. So don't be scared or start panicking if you get something like that and it's in the negative range. The gradient of this line, this would be our order. And this point here, what is that? Loud? That's the y-intercept, yeah. What does that represent?
C.
That's C.
The initial amount of the substance.
Careful. Careful. Look at what the C is here.
Okay.
It would be log K. Yeah? So this point here would be log K. So, for example, if log K equals, let's say, -2, what is K? How do we convert log into non-logs? Well, we take both sides, 10 to the power of, you have done that for the pH, so you would get K equals 10 to the power of -2. Yeah, so you can very easily directly read the rate constant, sort of directly read the rate constant from your graph. Are you happy with that? So just a little question for you, just to get the brain cells active. Let's say I have a speed 1 and I have a concentration of A. Yeah? And now I double the concentration of A and I get 2 times speed 1. Can you tell me what your gut feeling is? What is the order of this reaction? Sorry? It's a first order. Johannes says it's a first. Why?
As you double the concentration, you double the speed.
Doubling the concentration, if that results in double the speed, it is a first order reaction. You are absolutely right. Yeah? What would happen if it was a second order reaction and I double A? What would happen in this case? No? I know that you know that. I just want somebody else to give a chance to use their brain cells. What would happen? So if it is a second order reaction, what happens if A goes to 2A? Well, obviously, what we then have is really equals K times 2A to the power of 2. That's a second order reaction. And we can dissect that and say equals K times 2 to the power of 2 times A squared. And that is what we are looking for. So if we had a second order reaction and doubled the concentration, our speed would be 4 times the original speed. Yeah? Make sense? Fantastic. This almost certainly will hit you in the exam. where I say what will happen when. Okay, so we are happy with these graphs. You should be able to determine what kind of order a reaction is. So what I want to do with you today is really I want to talk to you about zero order reaction and then potentially about a first order reaction. So zero order reaction. And these reactions are quite common, zero order reactions, especially when we are looking at, for example, the elimination of a drug from the metabolism. Quite frequently, this follows a zero order reaction. The alcohol elimination from the body for a male, I have to say a male, follows a zero order reaction. The situation is slightly different for females. I don't want to appear to be sexist in any way, but I would say females are more complex. Have I navigated this cliff elegantly? Yes? Okay, good. So it doesn't apply to females. There are some interesting things going on with the metabolism. Now, in order to illustrate what this zero order reaction actually entails, it's basically we can write, if we have a reaction like that, we have a reactant A that is consumed in a zero order reaction. We can write the rate of the reaction equals minus K, because it's consumed, rate constant, times A to the power of 0. That's why it's a zero order reaction. And because A to the power of 0, anything to the power of 0 is 1, so we can write equals minus K. So in a way, you can look at it and say the rate is completely independent of the concentration of my reactant. And we can plot that, if you like. So if I, instead of rate, if I say speed, so I get rid of the minus thing, and here I plot A, the concentration of A, what I would find is basically something like that. It's constant. The speed is always the same. It doesn't matter what A is. Yeah? And we will find this particular case when we talk about enzymes. This happens to an enzyme reaction, and you've started with enzymes, haven't you? Do you like it? It's good stuff, yeah? There are lots of videos on my YouTube channel, for example, what Vmax and Km, what is Vmax? Yeah, what does that mean?
It means that the substrate occupies all of the sites.
Yeah, absolutely. The substrates occupy all of the active sites on the enzyme. The enzyme just simply can't work harder. It's a little bit like me. Can't work harder. What does Km mean? Yep. Km actually indicates the substrate concentration that gives us half of the maximum velocity. And Km makes a statement about how much the enzyme actually likes the substrate. If the enzyme likes the substrate, the Km is low, because you need only a little bit of the substrate in order to get half of Vmax. The affinity of the enzyme for the substrate is high. So Km low, affinity high. Km high, the enzyme doesn't like the substrate. Affinity is low. Yeah? And these things are on my YouTube channel, so if you want to have a look at that, please feel free. Okay, so how does a zero-order reaction actually work? Now, very simple. Let's assume I have a box of sweets. Let's assume there are 100 sweets in it. And I can eat 10 sweets in 10 minutes. This is actually my rate constant here. So 10 sweets per 10 minutes. How many sweets have I got left? Sweets left after 60 minutes. I like this part of the lecture. Who said what? 40? You said 40? Are you sure? How did you do that? 1 sweet a minute, yeah? Okay. Unless you don't like sweets. Okay, good, cool. So, we can actually do a little list and say, we start with 100 sweets, and every 10 minutes we take away 10 sweets. So, that's our T0 minus 10 gives us 90. That's after 10 minutes. Minus 10, 80, minus 10, so that's 20, 30, 40, 50, 70, 60, 50. You get the scheme, yeah? Here, what I take off is always constant. How would that look in, let's say, a graph? And you're absolutely right. After 60 minutes, only 40 sweets would be left. How does that look in a graph, in a graphical representation? Let's say I plot the time here, obviously in minutes, and my concentration of sweets, I call it A still, because it's a box of heroes. Tenuous, but never mind. So what would that look like, the graph? Can you describe it? It would be a straight line, exactly. So it would look like, let's say, if we start here, that's our T0, with 100 sweets. It would look like that, yeah? Something like that. There should be a straight line. What happens after 100 minutes? What would happen after 100 minutes? How many sweets have I left? 0. What happens after 110 minutes? Sorry?
You cannot extrapolate, so you can answer that.
Yes, I can answer that. How many sweets have I got left after 110 minutes? Still 0. Yeah? Unless I go to the shop and buy more sweets, but that's cheating. So it would basically look like that. Can I have negative sweets? unless I define pickled gherkins as negative sweets, I can't. So it would look like that. Yeah? Are you happy with that? Now I can turn this whole thing on its head, and I can say, if I have a graph where I plot concentration of A versus time, if I have such a graph and it gives a straight line, I know that it must be a zero-order reaction. If you think about it, a zero-order reaction gives me a straight line when I plot A versus time. What I'm saying is, if I plot a graph, A versus time, and I get a straight line, I know it's a zero-order reaction. Sort of exactly the same. Does it make sense? I sometimes give people data and say to them, demonstrate to me that this is a zero-order reaction. And all you need to do is use the data, plot the A versus time. Hopefully it gives you a straight line. And you say, because it is a straight line, I know it is a zero-order reaction. That's all you need to do. Are you happy with that? Fantastic. So zero order, we can deal with that. Now let's have a look at another very, very common reaction. And this is a first order reaction. Now, my claim is I have my chocolates here. Let's say I have my 100 chocolates. Sweets. And my claim is that I can eat, and here comes a subtle but very important difference. I can eat 10% in 10 minutes. Yeah? 10%. How many chocolates have I left after 40 minutes? How many chocolates have I left after 40 minutes? Let's assume I can't have any half-eaten chocolates. Yes. You make the decision. Sorry? Anyone? How many chocolates have I left? 65? 65. Yeah, I make it 66, but you know, that's. You're welcome. Usually, people in the back shout it out, and then I have to throw the chocolates, which sometimes leads to casualties. But luckily, this time, not so much. Right, how did you do that? By 0.9 each time. Okay, I show you how I do it, yes? I think I can understand where you're coming from. But let's do it sort of the pedestrian way. I start with 100. I remove 10%. What is 10% of 100? 10. Okay. So that's 0. That's after 10 minutes. How many have I left? 90. Now I remove 10% of 90. What is 10% of 90? Sorry? 9. So after 20 minutes, I have 81 left. What is 10% of 81? So I eat 8. Can't have a 0.1 sweet. So that would be 73. What is 10% of 73? Let's say it's 7. So that would be 66 after 40 minutes. Yeah? But I accept 65. What do you notice? Is what I take away, is that the same? Is that constant? No. This is not constant. Remember, in the zero order reaction, it was constant. In the first order reaction, it changes. And it changes depending on what I had previously. Yeah? Make sense? So, how can we actually describe that in a graph? And you probably have also noticed that what I take away becomes smaller and smaller. Yeah? So how can we describe that in a graph? Well, what we can do is we can do the concentration of A per time, say minutes. Try to figure out what the graph would look like from the data that you have. What would the graph look like? Is it a straight line? No. Is it a square? Is it a circle? What is it? Is a curved line? Absolutely. So it would look like, this is our 100 here. It would look like something like that, yeah? Oh, by the way, can I please ask you for the next session to bring some graph paper with you, because I want you to practice drawing graphs. Yeah? We will do that as a workshop. So this thing looks like a curve. Curves are horrible. I hate curves. And I want to point out this is not a misogynistic comment. Right? But curves, you can't do anything with them. A line is easy to extrapolate. A curve, God knows what happens in a curve. I also want to point out to you, will this curve, in an ideal world, will this curve ever reach zero? Theoretically not, because, okay, I said we are only dealing with whole sweets, but if I just have a little bit of sweet and then I just take a little bit of that little bit away and so on, it will never reach zero. It probably, my sweet left over at one point will be an accumulation of sweet molecules, but still, it's still there. It will never reach zero. So how can we deal with a curve? What do you do when you have a curve? Just from an engineering point of view, what do you do if you have a curve?
Do you draw like a line from the down to the x and make it form like a trapezium?
So what you do is, what you suggest is like that.
No, they'll put the second line down.
Like that.
Yeah,
Ah.
bring it down.
Mm-hmm. Now that's a little bit of a dilemma because, you lose information then of what's going on. What can you do if you've got a curve and you don't want a curve?
You make the same graph in a logarithmic scale.
A logarithmic scale. Okay, so you are one step ahead of me, which is great. If you have curves and you don't want them, you turn them into a straight line. Somebody's ass is ringing. So, you don't like curves, you turn them into a straight line. Have you done your Lineweaver-Burk plots already in enzymes? Yeah? Have you? Lineweaver-Burk plot? Eadie-Hofstee plot? Heinz-Wolff? No? Okay, good. This is exactly the same principle. In enzyme kinetics, you have a curve. You don't like a curve, so you try to turn this curve into a straight line. How do you do that? Well, in a way, and you don't need to repeat this because I give you the final outcome in a minute, but you basically write down the general rate law for a first-order reaction, which would be dA over dt equals minus k times a to the power of 1. That's the general rate law. Minus, because it's a consumption, k, that's our constant, and the rate order is 1. This is a differential equation, and those of you who have done maths A-levels will hopefully remember that you deal with differential equations by separating the offending variables, which are in this case dA and dt. So what you do is you bring dA, you leave dA on one side, equals minus k times, and you bring the a to the other side, so you have it like that, times dt. It's just simply rearranging this equation a little bit. And in order to get rid of a d of this differential, what you do is you integrate both sides. Don't worry, if I'm talking Chinese to you, you just simply integrate both sides. And what you get is actually an equation. And this equation for this integral reads ln of a at the time t, when you want your result, bless you, minus ln of a at the time 0, your starting concentration, equals minus k times t at the time t minus t at the start point. Looks incredibly complicated, and because I have sadistic tendencies, I want you to remember this equation. I'll show you some forms of these equations in a minute, which are a little bit more, how shall I say, user-friendly, which basically mean exactly the same thing. So how did this help us in this case? Well, it helps us because we can convert that into a straight line. We can say ln, that's the natural logarithm, ln of a at the time t equals, we bring this one here to the other side with a plus, equals ln a at the time 0 minus k times, now if we say t at the time 0, that's usually 0. That's when we start our observation. So a lot of people just simply ignore this t0. I will show you in the next workshop that sometimes it's good to keep it in. But we can say just simply t at the time t. So we ignored this minus t0 because usually it is 0. That's actually exactly the same equation as this one here, isn't it? I just played around with it. How does that help us? Y equals c plus mx. The straight line again. So what do we need to do when we want to plot that? Let me just quickly write that down again. ln a at the time t equals ln a at the time 0 minus k times t. So what do I plot? I plot my time here on the y-axis, on the x-axis, sorry. What do I plot on the y-axis? I plot ln of a. Yeah? What is this point here? The intercept with the y-axis. Loud?
LNA0.
It is ln a0. Exactly. Good man. You playing cricket? You should. So what does this graph look like? A straight line going down. Can it go into the negative range? Who said yeah? Who said? Nobody said. Yes, it can. Because it's ln. And ln can give you a negative value. You can't take an ln of a negative value, but you can have a value, a negative value from an ln. So this here is our lna. This here is our starting ln. What's the gradient? Sorry?
Minus k.
The gradient, absolutely right. The gradient is minus k. Yeah? Minus, it goes down. You deserve one now. The gradient goes down. That is what this minus says. And k is the rate constant. A little caveat, what people very often get wrong. K, the rate constant, is always positive. A negative rate constant does not exist. Negative rate order does exist. Negative rate order could be perceived as an inhibitor of a reaction. I'll come back to that another time. The rate constant is always positive. So please bear that in mind. Whatever you do, whenever you do it, whoever you do it with, a rate constant is positive. No exception. Right? So, let's see what we've done today. I have, let's say, a reaction. When I plot the data on an A versus T plot, A versus T plot. And I get something like that. A versus T plot. That's a straight line. Well, should be a straight line. What order is that? It's a zero order reaction. Why? Because it's a straight line. I have a first order reaction . How can I prove that this is a first order reaction? Sorry? Draw a graph, yeah, a good starting point. Draw a graph. What do I draw? A versus T. Do I draw A versus T? Natural log. Okay, who thinks I draw an A versus T? Hands up. Good, yeah. At least you stand your ground. What would I get with an A versus T? A curve, exactly. So A versus T, and I would get a curve. You are absolutely right. I can already say that this is definitely not a zero-order reaction, yeah, because in a zero-order reaction I would get a straight line. So you are right. Although I wouldn't be able to say that this is a first-order reaction, because that you would also get a curve if you had any other order. Yeah? So it's not proof. How can I prove it? If I plot ln of A versus T, and I get a straight line, then I know it is a first-order reaction. Yeah? That makes sense? This is usually a question in an exam. I give you some data, and 30 to 40% of the marks go to demonstrate graphically that this is a first-order reaction. What do you have to do? Well, you just do a graph like this one here. Say it's a straight line, and Robert is your mother's brother. Bob's your uncle. Problem solved. Every time I have a few specialists who say to me, okay, I draw an A to T graph, which is not wrong. It gives a curve. So therefore, it's not a zero-order reaction. If you're smart, and you're all smart here, because otherwise you wouldn't be here, you would know that this wasn't the question. I didn't ask you to tell me what it's not. I know it's not a zero-order reaction, and you know that it's not a zero-order reaction, because I already told you that it's a first-order reaction. So please, if you are asked to prove graphically, or to demonstrate graphically that it is a first-order reaction, don't waste your time on drawing something that's a zero-order. Give me the first order. ln time. Make sense? This is a question that some little birds told me will come up in the exam. Because so far, it has come up in every single exam. And there's a bloody good chance that it will come up again. Got it? Any questions? Have a lovely weekend. Be good. Don't do anything I wouldn't do.